Some about heat, right? Let's get to work. So let's say I've got this temperature reservoir over here, and that means it's like, it's got that temperature and it's big. So the fact is, you can't even see how big it is. It's just really big. And then we've got this, temperature reservoir over here, and it's got this other temperature, and they're different temperatures, and this is really big and that's really big, and they're not going to change their temperatures. That's the essence of a reservoir. And do you guys know how to spell reservoir? Is there an R in there? Reservoir or reservoir? There is an R. Okay, so this is on Anton, if this is spelled correctly. Reservoir, like that?
Actually,
uh-oh.
I don't think there's another E in there. I thought you were talking about the E at the end.
This R here, do you want this R or not?
Yes. Yes.
Okay. All right.
Is there
reservoir.
Is there
All
an E on
right.
that?
We'll look it up later. It's not important right now. What's important is I might have a tube going between these two things. Let's call it a solid hunk of metal. And I'm wondering, what do you think, what aspects of this tube would affect how quickly the heat can flow from one side to the other? Or maybe let me be more specific. How much heat has actually flowed from one side to the other? You want to propose some aspects of this that could affect it?
Probably density.
Density. Interesting. That's a characteristic of the material I don't really want to go into, but I'll leave that out to like how much the material conducts heat.
Pressure?
Pressure of this tube?
Yeah.
It's at atmospheric pressure. It's not going to be a fluid. We're not on fluids anymore. This is just a metal tube. Solid metal. It's like
length.
You think if the tube is longer, then less heat will flow or more heat will flow?
I want to say less heat, but...
So you think that the heat flow may be inversely proportional to length? Is that what you're saying?
Yeah.
Cool. What else?
Area?
Area. Do you think
Or
that...
does that have to do with length?
Well, I mean, I did draw a little cross section here,
That's true.
and so that is the area. So do you think a larger solid rod of some metal would conduct more heat or less heat?
Probably more.
More heat. Yep. Let's put area up in the numerator. What else you got? Anything else? 1 hour versus 5 hours? What's going to be more heat transfer?
Time.
Time. All right. What else? You're really close. There's just one more thing.
Velocity.
Was that a girl?
Kira.
The velocity of what? There's nothing moving here.
Speed of sound.
The speed of sound. I'm going to say, again, that's probably something to do with like density that affects the characteristic. I'll put it on here. This is the characteristic conductivity of the material. We're going to use it.
Constant?
It's actually a K, a constant of heat conductivity. Go on, I need something else. It depends on something else.
Gravity.
Was that a guy?
Yeah.
Oh.
Anton, that's a dumb answer.
Wow, that was a dumb answer.
Your guy voice does not sound like it.
We need to figure out what else affects the flow of heat. Can you think of nothing else that might affect how much heat goes between these two reservoirs? I'm going to tell you, but you'll be really embarrassed.
Jordan, we got this.
Mm-hmm. You're looking at it in my textbook.
I cannot see it.
It affects, well, come on, the difference in these temperatures. Of course, if these are very near the same temperature, then not much heat will flow. And of course, if they are very different temperatures, then a lot of heat will flow. So it's proportional to change in temperature and how much time has gone by. So really what I'm talking about is heat flow. We could define this thing called heat flow. That's actually all I've got for you guys, would be Q divided by delta T. So that's going to depend on the natural conductivity. This is the heat conductivity of the heat conductivity of the material, and it will depend on the area of the material that we've got through there, and it depends on the temperature difference, and it's inversely dependent on how much distance we have to get that heat across. So if this is a really short distance. So yeah, this is why fire doors are really, really thick. You want a thick fire door because you want to prevent the flow of heat through it, etc. That's it for that. There's this cool thing with, I mean, there are a lot of things that you can do with this, but I'm not going to do anything else with it right now. I want to talk a little bit about countercurrent exchange. I might have a hot, we can do it in purple. I might have a hot fluid coming out from my heart. Can you imagine that? That my heart over here is hot, and the fluid might be blood, and my body is pumping it that direction. And there's also like the, let's say these are the limbs. And the limbs are giving blood back to my heart, and the blood's going this direction, and it's a little bit cooler, right? So over here, the limbs are cool, and they have to remain cool. So what's happening here is the heart might be like 37 degrees Celsius or something, and the limbs might actually be room temperature. The blood at my fingertips is probably not much warmer than the room, so that might be something like 25 Celsius. But the cool thing is, we don't want to flood our hearts with really cold blood. That would be quite a shock to our heart. In fact, our heart would necessarily cool down if that were the case. But since these pipes are right next to each other, if you look in your arm, you got veins and you got arteries, and they're all kind of right next to each other. As the cool blood from the limbs goes towards the heart, it's exchanging heat with the hot blood that's leaving from the heart. So you get this heat. Let's see, which way would heat be going? Would it be going down or up during this time?
It'd be going down.
It'd be going down, yeah. Heat is going down this whole time. So in fact, it's probably a steady heat going down. As this blood goes out to the limbs, it's cooling, and as the blood is coming back from the limbs, it's warming. And this technique is really, really a handy technique. It happens in a lot of designs. In some designs, you wouldn't want to have countercurrent exchange. You wouldn't want to have countercurrent exchange with an air conditioner, for instance, because the air conditioner is designed to take heat out of the house and dump it way out of the house, and then the cool fluid comes back into the house and you blow a fan across it. Does that make sense? Okay,
Yeah.
that's all I want to say about that. One more thing, and we'll end the chapter in heat, and it is the Stefan Boltzmann law. The Stefan Boltzmann law for radiated power. The power radiated by anything because of its temperature is, well, it's E times sigma, boy, that's looking pretty good, right? Times the area of the thing, this is surface area. So it makes sense that things that have a larger surface area are going to cool faster, right? This is why you can take a little scoop of your soup and bring it up, and it will cool faster than the whole bowl of soup, because the whole bowl of soup has a huge volume and not a lot of area. But if I bring up just a scoop of soup, then it will cool quickly. It's also why inside of my computer I can find a thing that's shaped like this. That's designed to maximize surface area. It's a heat sink. So radiated power is larger when the area is larger. And radiated power means that the heat is leaving the thing that is hot. And of course, it also depends on how hot that thing is. But this is the most amazing law in the entire universe. It doesn't depend on temperature. And it doesn't depend on temperature squared. And it doesn't depend on temperature cubed. It depends on the fourth power of temperature. This is the most insane dependence of anything on any physical quantity that I've ever heard of. But we need to address these other two variables. This guy right here, sigma, this has something to do, ooh, what could sigma be? What could sigma, let's talk about E. E is a number that's in between 0 and 1, and it talks about how emissive the surface is. So an E of 0 would mean very shiny or very white. So those materials are not very good at radiating heat because they actually trap heat inside of them. They're also not very good at absorbing heat. E is very much a symmetric thing. So it's not, something that is a good radiator of heat is also a good absorber of heat. This is why you can find people in the heat of Africa who are wearing black clothing, because they want to radiate the heat that they're getting. And if you're in the shade and you're wearing black clothing and it's a hot day, you're gonna feel a lot cooler. So it's a really neat technique. And we could also talk about E of 1, which would be something that is black. It turns out that at the frequencies at which we're discussing, like my human body, I am as black as any other person in the infrared. Awesome. We are all the same amount of black, which is quite a bit black, because we are very near E equals 1 for the temperature of our body. So that's awesome. And sigma, it's just a constant. What do you want? You want sigma? Here it is. Sigma is 5.67 times 10 to the, what, -8th. and it's got units. I guess it's going to be watts because that's the unit of power. And then we have to divide by the units of area. And we have to divide by the units of temperature to the 4th. Dang. Okay, so we're gonna play with this law a little bit too. Goodbye. This is on Anton, if this is spelled correctly. Reservoir, like that?
Actually,
Uh-oh.
I don't think there's another E in there. I thought you were talking about the E at the end.
This R here, do you want this R or not?
Yes.
Yes?
Okay, all right.
Is there
Reservoir,
Is there
all
an
right.
E on that?
Some about heat, right? Let's get to work. So let's say I've got this temperature reservoir over here, and that means it's like, it's got that temperature and it's big. So the fact is, you can't even see how big it is. It's just really big. And then we've got this, we've got this. We'll look it up later. It's not important right now. What's important is I might have a tube going between these two things. Let's call it a solid hunk of metal. And I'm wondering, what do you think, what aspects of this tube would affect how quickly the heat can flow from one side to the other? It's temperature reservoir over here, and it's got this other temperature, and they're different temperatures, and this is really big and that's really big, and they're not going to change their temperatures. That's the essence of a reservoir. And do you guys know how to spell reservoir? Is there an R in there? Reservoir or reservoir? There is an R. Okay, so, or maybe let me be more specific. How much heat has actually flowed from one side to the other? You want to propose some aspects of this that could affect it?
Probably density.
Density, interesting. That's a characteristic of the material I don't really want to go into, but I'll say, I'll leave that out to like how much